Hi guys, welcome to another lecture in the series Organic Chemistry 1. And today we'll be speaking mainly about the methods of determining reaction mechanisms. Of course, my name is April Johnson. So the determination of the pathway of a reaction mechanism is a mystery to be solved. To solve the mystery, the scientists will make observations, that is, look for clues into what could be the pathway. We're going to propose a hypothesis, and then we're going to test the hypothesis. So since the mid-1800s, a great deal of research has been conducted to determine the pathways by which the organic reactions occur, right? So we know our starting material, we know our product, right? But what pathway, how did we get from our starting material to our product? How do we know which bonds were broken and formed from going from A to E, as we see here, right? What are the intermediates? Did it just go from A to E, or are there intermediates along the way? So these are the questions that would cause any scientist to want to figure out these reaction mechanisms. So in some cases, we are able to identify the intermediates, right? Some of them are stable enough to be isolated from the reaction, and thus they can be identified. This is, however, not common. More often, the existence of intermediates is inferred from spectroscopic data. So we look at the spectroscopic data and we can say, okay, perhaps this is the pathway that the reaction took. So today we're going to look into 4 of these methods of investigating reaction mechanisms. So we're going to start with the spectroscopic methods, which looks at the nature of the products or the intermediates. Then we're going to look at the stereochemical evidence, whether it's cis, trans, etc. For the third one, we'll look at the kinetic evidence, the rate of the reaction and how varying a particular reactant will affect the product. And then finally, the use of isotopes, whether or not we're substituting our carbon 12 for carbon 13, or carbon 18 for or oxygen 18 for oxygen 16, etc. So all of these methods will give us clues into our reaction mechanisms. So the first one that we look at is the nature of products or intermediates. That is spectroscopic methods. All right, so here we're looking at this reaction, which is the condensation of a carbonyl compound with hydroxylamine to yield an oxime derivative, right? So we have either aldehyde or a ketone here, which is represented by the fact that we have a carbonyl, which is C double bond O, and 2 R groups. Whether it's 2 carbons or a carbon and a hydrogen, that's fine. And we have our hydroxylamine here, and then that forms our oxime and water. So to investigate the mechanism of this reaction, we need to look at the nature of the products formed, right? So we're looking at, okay, we have a new bond here between our carbon and our nitrogen. And then we're looking at the fact that water is formed. All right, so this is a color-coded scheme, right? So we're showing the new bond between the carbon of the carbonyl and the nitrogen of the hydroxylamine, and we're showing the water as we saw previously. Now, the condensation suggests that some point in the mechanism, a molecule of water is removed from the reaction intermediate. So let's look at this mechanism that is proposed, right? So here, this is a kind of a generic mechanism where R for us represents the hydroxyl group, right? Or hydroxylamine is what we're saying is represented here, right? So we start off with the nitrogen being nucleophilic and the carbon of the carbonyl being electrophilic, right? So we expect this reaction at first. One, because our product has a nitrogen carbon bond, that gives us some clue, even if we didn't know that our amine is nucleophilic, right? So this carbon oxygen bond, or at least one of the bond, is broken, which is represented by the arrow starting here. And remember, wherever the arrow starts is the origin of the electron, wherever the arrow ends is where the electron is going, right? So we must have that basic understanding and knowledge. So because the electrons ended up on the oxygen, here we have our dipolar intermediate where we have a negative charge on the oxygen, a positive charge on the nitrogen, right? And then from our dipolar intermediate to our amino alcohol, we have a proton transfer occurring, right? So a proton is transferred to our oxygen, which gives us our amino alcohol. Now, from our amino alcohol to our protonated amino alcohol, right? We have acid here, so our oxygen can be nucleophilic and abstract a proton from our hydronium ion to form our protonated amino alcohol. And then as we saw in the product, we have a double bond between carbon and nitrogen, and so that double bond will form here, and then we have loss of water, right? So based on our nature of our products, we have loss of water, and therefore that must be reflected in our mechanism as we see here. So we have our iminium ion, and then the final step is just for the water to abstract this proton and quench positive charge, and we end up in our case with an oxime, right? So here we have our new bond, our double bond between our carbon and our nitrogen. We still have our nitrogen hydroxyl group, and then we have water as this water left. That's an important point of the mechanism. All right, so spectroscopy is very important in the process, right? So if we monitor this reaction using IR spectroscopy, right, we will see, and if we recall, our carbonyl group here will have a wave number of about in the 1700 region, and for our imine that will be in the 1665 region, right? And so if we're monitoring this reaction with IR spectroscopy, we will see a disappearance of the carbonyl stretch, right? And then the appearance of our imine stretch, right? So this is what we will observe. Carbonyl stretch shrinks to nothing before imine stretch begins to appear. And we can compare our starting material with our product. So our product will have the hydroxyl at 3600, right? That is our OH functional group, and to a lesser extent our NO at 945, right? So here the key thing is here, when we're monitoring this reaction via IR spectroscopy, we will see a disappearance of our carbonyl peak and the appearance of our imine and our hydroxyl peak. All right, so just a reminder, right, of some of our stretches and the types of peak we will see. So our OH stretch we will see here, right? And so what we're saying is that the starting material will have our carbonyl stretch, which is in the 1700 region. So we're saying that this will diminish and we will see the imine peak in the 1665 region, and then our hydroxyl peak. Our hydroxyl peak, let's look at it again. We'll see the hydroxyl peak from our hydroxylamine at 3330, right? And then our oxime hydroxyl will be in the 3600 region. All right, so it will still be in similar regions, but the wave number is different. So that leads us to our first question, which is, for the following reaction, suggest how the nature of the products gives details about the mechanism. Right, so just take a minute, pause, and answer or attempt to answer this question. But what we're looking at here is, we have a chiral center here, and in the presence of acetone and water, we get a racemic. So this plus minus suggests that we have a racemic mixture here. Sorry. So our answer to that question is, when we compare the starting material with the product, we notice that it's a substitution reaction, right? Because bromine was substituted for the hydroxyl group. The plus or minus symbol, as I said, suggests racemization, and so the mechanism must be a SN1 mechanism, right? Also, the possibility of a very stable resonance carbocation intermediate, right? So that intermediate kind of gives more validation to the SN1 being the mechanism for this reaction. And just to add to that, if we're going to look at it, from a spectroscopic point of view, if we look at the reaction, if we monitor the reaction, right, we will definitely see the appearance of the hydroxyl group, right? If we're going to use IR, for example, to figure out, which product is formed, etc., or to give us insight into the reaction mechanism. So our follow-up question 1 is, write out the SN1 mechanism for the reaction in question 1 and include the various resonance, or we say canonical structures, of the benzyl carbocation. So again, write out that SN1 mechanism and include the various resonance forms of the benzyl carbocation. All right, so the next topic that we're going to go into is the stereochemical evidence. And we have touched on that, when we're answering this question, right? Because the stereochemistry of the product was one of the key things that gave us insight into the reaction mechanism. So we're going to look at another example of stereochemical evidence, right? So here we have an alkene, cycloalkene. In the presence of bromine or any halogen, right, we can get either the cis product or the trans product. The fact that the trans product is the only product that is formed gives us very strong evidence into this reaction mechanism. So just in case you have forgotten, right, let's just look at it. So here we have, any alkene in the presence of the halogen, it becomes polarized, right? So we have our delta positive and our delta negative. And you know, the one of the bromines attaches to the double bond, right? So the double bond is nucleophilic, the bromine is also nucleophilic. So we have this bromonium ion being generated here, and we have the loss of a bromide ion as seen here. And then our step 2 suggests that the bromide anion attacks at the back side of one carbon or the other of the bromonium ion in a SN2 reaction, causing the ring to open and results in the formation of the trans dibromide, right? So because of where the bromide ion attacks, right, it suggests that, okay, we get the predominant product is the trans product for this particular reaction that we're looking here. So the important point here is that because of this stereochemical evidence, right, the fact that we got only the trans product, it gives us insights into the reaction mechanism. All right, so here we're seeing on screen the X-ray diffractometer. So some bromonium and iodonium ions have lifetimes long enough to allow their crystallization and X-ray analysis. So remember what we said previously, that it's very uncommon to isolate an intermediate, right? So this is one of those uncommon situations where using this instrument, they're able to analyze by X-ray analysis the intermediate for the reaction. So that bromonium ion, yeah, this is iodine, but they're able to observe this intermediate. That is amazing, right? So using the X-ray diffractometer, they're able to look at the intermediate for this particular reaction. So the third area that we're going to look at is kinetic evidence. All right, so here we have a reaction of an alkyl halide with a base, right? And we have the formation of a double bond of alcohol and sodium chloride. So the rate of the reaction can be investigated with respect to the change in concentration of one or more reactants. So here, you know, we have a very strong base in the form of the methoxide ion or sodium methoxide, right? And it can abstract a proton, which will then form the double bond and then kick out the halide, right? So we have the chloride being eliminated. And so the rate is actually equal to K, which is the rate constant, times the multiplied by the concentration of the alkyl halide, then multiplied by the concentration of the base. So the rate is dependent on both reactants here. So the observation, the rate or the reaction rate is proportional to the concentration of both reactants. So now we're going to look at another instrument, which is, we just looked at the X-ray diffractometer. Now we're going to look at another instrument that can help us with the kinetic evidence. So let's talk about it a little bit first. So the stopped flow is a spectroscopic technique used for studying fast reaction mechanisms in solution over time scales of about 1 millisecond up to about hundreds of seconds, right? So two reagents are rapidly mixed together and then stopped in an observation cell. The sample is irradiated with monochromatic light, and as the reaction proceeds, the change in the recorded signal is usually the absorbance of a specific wavelength, right? So that is recorded as a function of time. The analysis of the data can be used to, one, determine reaction rates, right? It can also use to determine the complexity of the reaction mechanism. Okay, so and it can also use to help us with the kinetic evidence that we're talking about here, which obviously would be the reaction rates. And adding to that, right, the information on short-lived reaction intermediates, yes, so it can give us information there. So just to recap what we just saw a while ago, the stop flow, and we're going to look at how it looks in a little bit. It is a spectroscopic technique that is used for studying very fast reaction mechanisms, and up to 1 millisecond they can study these very fast reactions. The two reagents mixed together, stopped in an observation cell. The sample cell is irradiated with light, and then they can get information based on the absorbance at a specific wavelength, right? So they can determine reaction rates, complexity of the reaction mechanism, information on short-lived intermediates. So this is how the instrument looks. You have two syringes, right? And they're here. This is how it looks in real life, and then animation or picture form here. So you have the injection syringes, right? And then you have the mixing chamber, which is where it is stopped. You measure information about it, and then the reaction proceeds over time. So that leads us now to question 2, which says, what kind of mechanism is this? So the reaction that we looked at just now, what kind of mechanism is it? So pause and look at it. All right, so if you answered it's an E2 mechanism, you must state why you think it's an E2 mechanism. So if you say that it's concerted bond forming, bond breaking, if you said the rate is dependent on both reactants, if you said ATL was eliminated from the alkyl halide, and if you say that, okay, well, we have a strong nucleophile, all of these things suggest the E2 mechanism. Our follow-up question 2 is, what is the rate equation for the E1 mechanism? All right, so the other portion of the lecture, the fourth one, is the isotopic labeling. So for isotopic labeling, the mechanism of a reaction can be studied by determining the bonds, which bonds are broken, which bonds are formed in a particular step. And isotopic labeling assists with that, right? So the first example that we're going to look at is that of base hydrolysis. So if you recall saponification, which is, the hydrolysis of ester in base, it's named after the Latin word sapo, meaning soap. So soap, and that is why I have the picture of the soap here, is made from boiling animal fat. So these triacyl glycerols, right, with base, such as sodium hydroxide, and then we have soap, right? So basic hydrolysis occurs through nucleophilic acyl substitution pathway, and we can use isotopic labeling experiment to support the mechanism. So essentially we want to see which bond is broken. Is it the cleavage of the carbon-oxygen bond, or the cleavage, like which bond is broken? And perhaps I should draw it out here. So all right, so we're back in business. All right, so we have the oxygen. So essentially we want to know which bond breaks, right? So is it this bond, or is it this one, right? So is it the black or the red? And so isotopic labeling will help us to figure out which bond is the one that breaks, and therefore that will give us insight into the mechanism. All right, so here we have this ester, right? We have this ester, and here we're seeing that this is the bond that's broken. This carbon-oxygen bond, this is the bond that's broken. And so what we're looking at here is the labeling. So anywhere that you see the asterisk, that is where the labeling. So what kind of labeling are we talking about? Normally we have oxygen 16, right? So if we change our oxygen to oxygen 18, right, and then we follow the reaction to see, if we inspect this compound and we see oxygen 18 here, then we can have an insight into which bond broke, right? So clearly oxygen 18 is on the alcohol, right? So that suggests to us that this is the bond that is broken. And if it's not clear right now, hopefully it will get clearer as we go along, right? So this is the mechanism that is proposed here. We have our base, so we have our sodium hydroxide, so we just have our hydroxyl anion here, which is nucleophilic, attacks our electrophilic center, carbon-oxygen bond breaks, forming our negatively charged oxygen here. Pair of electrons reforms or double bond, and then we have loss of our very good leaving group or ethoxide, right? And then we have another molecule of ethoxide, which was eliminated here, abstracting our proton to form negatively charged oxygen here, which then abstracts a proton from our hydronium ion to form our carboxylic acid, right? So here, this mechanism supports this carbon oxygen being broken, because at the end of the day, right, if we label the oxygen with oxygen 18, right, this oxygen here, then if it ends up in the ethanol, then that supports this particular mechanism that this carbon oxygen bond is broken and not the oxygen ethyl bond. All right, I hope that clears it up. All right, so another example into isotopic labeling is the Claisen rearrangement. I hope you have met this before. So for the Claisen rearrangement, right, I'm sure you can see here that we have this ether here, and then for the products, it's generally formed by heating, right? So you have this ether, and then you heat it and you get, you know, this phenolic derivative. Okay, all right, so what we're seeing here is that this bond is broken, right? And that should be clear that this bond is broken and this bond is formed, right? So the question is, does the reaction occur via a pericyclic or ionic mechanism? And you might be thinking to yourself, okay, ionic sounds familiar, but what is pericyclic? So what is pericyclic? Pericyclic reactions are any concerted reaction in which bonds are formed or broken in a cyclic transition state. So electrons move around in a circle. That is, there is a single transition state from start to finish, in contrast to a stepwise mechanism, right? So here we have our starting material or product, and we just have a transition state, and that occurs in several other reactions that we have looked at, you know, our SN2 and our E2. We just have a transition state and then our product. Unlike, you know, our SN1 or E1, we have an intermediate, usually our carbocation intermediate, right? And then we have our product, right? So the pericyclic reactions would be somewhat similar to our SN2s or E2s, where we just have a transition state and then the product. So let's look at the first. So we're going to look at mechanism A and mechanism B. So A is our pericyclic mechanism and B is our ionic mechanism. All right, so here we have, you know, let's just state here that pericyclic reactions are usually rearrangement reactions in which the transition state of the molecule has a cyclic geometry and the reaction is concerted, as we mentioned earlier. So here we have, you know, this bond, carbon-oxygen bond, being broken. So we form a double bond here. One of the bonds here are broken to form this single bond here. One of these bonds broken to form a double bond here, right? So we have a cyclic geometry, and we form this product, right, which basically rearranges, so the aromaticity is regained by keto-enol tautomerization. That should ring a bell, guys. So this is keto, right, and then it has been transformed, so they are isomers, right? So this is the ene and the ol, so it's called keto-enol tautomerization, and that is how aromaticity has been regained, right? So we reform the double bond here, pull a proton, and then we end up with our product, right? So this is the mechanism A, which is pericyclic. We just have a transition state and then the product. So our mechanism B is ionic, right? So for this ionic mechanism, we're saying that, you know, this bond breaks first to form this intermediate, which is a carbocation intermediate. And then after it breaks, we have a reaction between the benzene ring and the carbocation, right, which quenches a positive charge. and then after which we have rearomatization to form our product, right? So let's look back at our pericyclic reaction. So here we're saying it's a cyclic geometry, and it's a rearrangement of sorts, right? So we form a transition state and it is concerted. Here we're not seeing a concerted reaction, we're seeing steps, right? We're seeing the formation, this bond breaking, we have intermediates, right? And then we have products. So at this point, you know, we're saying that, notice this arrow, right? This is a resonance arrow. So we're saying that this double bond, this plus charge is resonance stabilized, and so, you know, this is the same as this, just that, you know, how we draw the electrons differ, which is why we call them resonance structures. And the attack happens here, or it happens here, right? So the point of this particular slide, and the reason why we're seeing the asterisk, is because we're looking at carbon labeled with carbon 13. So we're saying here that a mixture of products would be formed with the carbon 13 label scrambled at the electrophilic aromatic substitution step, right? So this is the EAS step, right? So we're saying here that if this bond breaks, this carbon oxygen bond breaks, then the attack can either happen here at this carbon or here. So we're seeing an example of both attacks, right? So in the upper reaction, it happens at this carbon, and in the lower reaction, it happens at the other carbon that is not labeled with carbon 13, right? So this is isotopic labeling, remember? So the isotope that we're used to, that is most abundant, is the carbon 12. If you label one carbon, one particular carbon with a particular isotope, then we would have a mixture of products, right? So here we're seeing the product where this carbon is bonded to the benzene ring, as opposed to this carbon that's bonded to the benzene ring. All right, so I hope that is clear. So at the end of the day, we're going with one mechanism, and the one that is correct is mechanism A, which is the concerted mechanism. And that is because only one product is observed. That is the carbon 13 labeled carbon 1, right? So notice, let me go back to this slide. We would have gotten a mixture of these products, right, had it been mechanism B. We only got one product, right? Only one product is observed, right? And that's, I labeled this carbon 1, carbon 2, carbon 3, and what we're seeing here is that the product in which you have a bond between the carbon and carbon 3 was the only product that was observed. No scrambling was found, meaning you didn't have a mixture of, you know, one carbon 1 being bonded to this carbon and carbon 3. We only had carbon 3 bonded to the aromatic ring. And the analysis was carried out using carbon 13 NMR. NMR stands for nuclear magnetic resonance. So when carbon 3 was labeled, previously we saw where carbon 1 was labeled. So when carbon 3 was labeled, right, we saw that this was the only product that was observed, which corresponds to an intramolecular product. This intermolecular product, which would have been the product formed from an ionic mechanism, was not observed. The intramolecular product was the only product that was observed. So today we're looking at, a few instruments, right? We saw the X-ray diffractor earlier, we saw the stop flow spectrophotometer, and now we're looking at the NMR spectrometer, right? And this is how it looks, a very big instrument in comparison to the stop flow instrument that we saw earlier, right? So we don't really need to go into how it works, at least at this stage, but just to look at the instrument and the data in which it presents to us, right? So going back to this slide here, we said that the analysis was carried out using carbon-13 NMR. And this is what it looks like, right? So this is the carbon-13 spectrum of the product, right? So here, and you will meet, or we're going to do spectroscopy next semester, right? So you will understand what these numbers mean then. So at this point, I know that you have no idea what these numbers mean. So we're just going to extract the information at this point, right? So we're saying if scrambling label at 115.9 and 33.6 would be enhanced, right? So look at the ppm down here. We're looking at the 33.6 peak, which is here, and it corresponds to this carbon here. And we're looking at the 115, this is 10, so this is 115.9 peak. These are the two peaks that we're looking at, right? This and this. And we're saying that if there was scrambling, if we got this products, that is the products from the ionic mechanism, then both this peak and this peak would be enhanced. However, we only saw enhancement of the 115.9 peak, that is this one, right, which suggests that this is the only product that was formed. There was no scrambling, meaning there was no ionic mechanism. There was a concerted pericyclic mechanism. All right, so that leads us now to question 3, which says, observing the reaction that we see here, how can isotopic labeling help us to figure out the above reaction mechanism? So let's look at this. We're seeing here that the oxygen 18, so we have replaced this oxygen isotope with the oxygen 18. And we're seeing here, this suggests that this reaction was not successful. And so this was a successful reaction in which the oxygen that was labeled with the oxygen 18 is bonded to the carbon of this carbon here, right? So this suggests that there's now a new bond between this oxygen and this carbon. Why am I answering it? Take a second, answer the question. So how can isotopic labeling help us to figure out the above reaction mechanism? Well, if you wrote that the oxygen on the alcohol is labeled with oxygen 18 isotope, right here, so we must look to see where it ends up. Is it in the ester of the final product, or is it a part of the water molecule? So is it here on the ester, or is it on the water molecule? So as we can see, this reaction didn't happen. So what happened was the upper reaction, which is here. So it's on the ester. So the mechanism must involve, right, the loss of the hydrogen from the alcohol. So the mechanism must show that this hydrogen was lost, and the mechanism must also show the loss of the OH from the carboxylic acid, right? From here, this is COOH. So the mechanism must show the loss of this hydrogen and this OH, right? And must also show the formation of the new bond between this oxygen and this carbon, right? So going back to the question, it says, how can isotopic labeling help us figure out the above mechanism? Well, it gives us some insight into which bond broke and which bond formed. It definitely told us that the bond formation is between the oxygen 18, the labeled oxygen, and this carbon here, right? So our mechanism, it gives us insight because our mechanism must show the loss of water via this hydrogen and this OH. So I'm sure you would have expected this follow-up question, which is propose a mechanism for question 3. The question, what we just spoke about, that mechanism that must involve the loss of the hydrogen, this hydrogen, and this OH, right? So propose a mechanism for question 3. And then the second question is draw both the ionic and the pericyclic mechanisms of the Claisen rearrangement. So this is a lot of practice here in this question, right? This is practice. Propose a mechanism for question 3 and draw both the ionic and the pericyclic mechanism of the Claisen rearrangement. All right, so now we're looking further at, the isotope, but something a little different. We're looking at the kinetic isotope effect that we will call the KIE. So when the rate limiting step in a reaction involves the breaking of a bond, so we're looking at an arbitrary AB bond here, the replacement of atom A by an isotope of higher mass will result in the reduction in the reaction rate. And this is called the kinetic isotope effect, or KIE. So normally it is, and we're defining it now, as the ratio of the rate constants for the reactions involving the light isotope, which we will call KL, and the heavy isotope, which is KH, right? So KIE, which is kinetic isotope effect, is equal to the rate constant of the reactions involving the light one over the heavy one. So this happens because the bond strength increases as the atoms is replaced by an isotope of greater mass, right? And so this kinetic isotope effect is most clearly seen with protium, or the hydrogen that we know of, and it's replaced by deuterium, and the maximum value for the KIE here has been calculated to be about 7 at 25 degrees Celsius. All right, so let's look at this reaction here. So here we have base abstracting a proton to form a carbanion, right? And I'm sure we've seen a similar reaction to this already, right? So the rate of this, the rate constant would be Kh, right? So if we replace one of the hydrogens with deuterium and then measure the rate constant for this would call Kd, and then we would divide both rate constants, and in this case the value is 6.1 at 25 degrees Celsius. So this change in rate is not limited to protium and deuterium. The maximum values of the KIEs observed with other isotopes are seen here, right? So for hydrogen, proton and tritium, that is a whopping 13 in comparison to carbon, oxygen, and chlorine, where these are very low values of 1.1, 1.01, 0.2, and 0.7. So we can see here that the isotopes of hydrogen the change is more significant than these other isotopes. So that leads us to question 4, which says the equation for the reaction between bromine and 2-phenyl propane under ultraviolet light is shown below. When the hydrogen atom labeled with an asterisk is replaced by deuterium, the rate reaction slows to approximately 25% of its original value. And the question is, why is this? So take a second, look at the reaction, and propose a response. Well, if you had all of these things that we mentioned earlier, that is, the rate constants, if we divide them, that's between 6 and 7 at 25 degrees Celsius, right? Or at, whatever temperature we're measuring at. And if you had that the rate limiting step in the reaction involves the breaking of the carbon-hydrogen bond, the replacement of protium with deuterium, which is a higher mass isotope, will result in a reduction in the reaction rate. And this only happens because the bond strength increases as one of the atoms is replaced by an atom of greater mass. So this is a full response as to why the speed of the reaction will slow down. So the follow-up question 4 is, why is hydrogen most often used to observe the KIE? So we're comparing it to other elements. All right, so the final part of the lecture has to do with kinetic versus thermodynamic control. So this is a subtopic that is of importance to you because you study pharmaceutical sciences. So sometimes the product ratio from a reaction can be changed by altering the conditions, right? So the two important terms here, the kinetic product, thermodynamic product. So the kinetic product is formed faster at lower temperatures, while the thermodynamic product is more stable and formed at higher temperatures. So the example that we're using is that of naphthalene, and it is converted to its corresponding arenesulfonic acid when the former is heated with fuming sulfuric acid, or sometimes you will see oleum as opposed to sulfuric acid. Another thing that I want to point out in that regard is, sometimes you will see F and sometimes you will see PH, right? So one is the British spelling and one is the American spelling. So pardon me, but you will see both on the slides, right? So one is British, one is American. So that is the spelling, right? F versus pH. So one of the isomeric sulfonic acids will predominate under different conditions, right? So in the presence of oleum or sulfuric acid and naphthalene, you will get either the 1 sulfonic acid or the 2 sulfonic acid. And so based on the conditions, we get either the kinetic or the thermodynamic product. So let's recall the sulfonation of benzene, right? Do you remember? Electrophilic aromatic substitution, EAS for short, right? So we have benzene, and we've seen nitration, we've seen sulfonation before, and if you don't recall, please go and check that out, right? So the electrophile is generated here, right? So from sulfuric acid, we have our electrophile sulfonium ion being generated. Once our electrophile is generated, we have electrophilic aromatic substitution, and perhaps if you want to do an exercise, you can draw the various resonance structures of this areneum intermediate. But at the end of the day, you have substitution of the hydrogen for to form sulfonic acid. So in a similar fashion, when we react naphthalene with under sulfuric acid conditions, you will have the formation of sulfonic acid. However, depending on the conditions, you will get either one sulfonic acid or 2 sulfonic acid. So what are these conditions? So when the reaction is carried out at 80 degrees, the major product is the naphthalene 1 sulfonic acid seen here. However, at 160 degrees, you get 2 sulfonic acid. It is preferentially formed. So the higher, remember what we said before, the higher temperature gives us the more stable thermodynamic product. Let's go back to it just in case you have forgotten. The thermodynamic product is more stable and formed at higher temperatures. The kinetic product is formed faster at lower temperatures. So here we see our kinetic product. It's formed faster, even though we're not seeing the rate here, but it's definitely at a lower temperature. All right, so let's look at the energy profile diagram. So we have our naphthalene seen here, we have our kinetic product and our thermodynamic product, right? So our areneum ions, notice that they're different in energy. So this is of a lower energy, right? And therefore that is why the kinetic product is formed faster than the thermodynamic product. That activation energy is higher in the thermodynamic product, but once it crosses that, it's definitely more stable than our kinetic products. That is, it's lower in energy. All right, so now we're looking at the heat of formation data, and we're comparing, the 1 sulfonic acid with the 2 sulfonic acid, and we're seeing here that, they're not very different, but different nonetheless, right? Minus 315 versus minus 333. And then we're looking at the areneum ion, also seeing some differences there, 471 versus 467, right? So that gives us some insight, from an energy perspective, between, the rhenium ions as well as the final product. So the formation of the one substituted rhenium ion is faster, it's formed faster as the intermediate is more stable. And the question is why? And it's stable because the more stable canonical or resonance forms can be drawn for this species than the two substituted rhenium ion. So we're going to look at it in a little bit more detail in a little bit, but just to say and just to accept at this point that the one substituted rhenium ion is formed faster as this intermediate is more stable. Why? Because the more stable canonical or resonance forms can be drawn for this species than the two substituted rhenium ion. So notice here that, yes, we have 1 and 2 rhenium ions here, right? But what is significant here is that we have a fully intact benzene ring, right? And then if we draw the other resonance structure for this, if we put in our arrow here, and let me try to do that quickly. Right? So in going from here to here, right, would form a positive charge here, and our benzene ring stays intact for this particular intermediate. And also the naphthalene 2-sulfonic acid is more stable than its one isomer. Why? Well, this is because there is no steric interaction between the sulfonic acid group and the perihydrogen in the two substituted product, right? So this is the perihydrogen, and we're saying that this one, there's no steric interaction between the sulfonic acid group and the perihydrogen in the two substituted product. And that is why the naphthalene 2-sulfonic acid is more stable than its one isomer. So just to go back to the energy profile diagram, just in case you might be a little bit confused, right? So we're saying that for the final product, right, this product is more stable than this, right? For the rhenium ion, we're saying for the kinetic product, this rhenium ion, this one, is more stable than this one, right? So to be clear, again, our rhenium ions, the one for the kinetic product, is more stable. That is this one, lower in energy. For our final product, that is the sulfonic acid, the 1 versus the 2, we're saying that this is the more stable product versus the 1, right? So that is why on this slide, we're talking about the rhenium ion. Why is this one more stable than the other one? And we're seeing here because you have more stable canonical forms. You have more stable canonical forms of this intermediate than the other one, right? And then for the final product, we're saying that the 2-sulfonic acid is more stable than the 1 because of steric, we're looking at the steric interaction. So for the 2, where the sulfate group is here, there's no steric interaction between the sulfonic acid group and the perihydrogen, which is here. All right, so hope that is clear. So this leads us to our final question, which is our question 5, which says write out all of those resonance structures for the 1 and 2 substituted areneum ions for the electrophilic aromatic substitution of naphthalene with sulfuric acid / nitric acid, right? So we're looking at a nitration of naphthalene, and write out all of those resonance structures for both the 1 and the 2 substituted areneum ions. All right, so please take a second, pause, and answer this question. All right, so if you drew out all of this, wow, good job. So let's look at, in particular, when we're looking at the stability of the areneum ion, let's look at these. All right, I'm backtracking a little bit. All right, so let's look at both areneum ions and the different resonance structures. So it would be nice if you actually put in your arrows, right, to go from one intermediate or to one resonance structure or canonical form to the next, right? So from here to here, we're drawing our arrows from this double bond to the plus charge. And then from here to here, we're drawing our arrow from here to here. And then from here to here, we're drawing our arrow from here to here. And then we end up, so we do that and go all the way around, and we do that for all of them, right? So please ensure, just put in your arrows so that you can properly document and follow the movement of electrons. And remember what we said about the resonance structures. We're saying that the electrons are delocalized, so it's moving all around. So again, don't just draw these, draw your arrows so that you can account for the electron movement. And then our final follow-up question is count the number of canonical or resonance structures with the benzene ring intact for both the 1 and 2 substituted areneum ions. So you're going to go back to the previous slide, and then you're going to count how many of those canonical or resonance structures has the benzene ring intact. And that should give us some insight into the stability, or to compare the stability of our areneum ions. Okay, so again, thanks so much for reaching the end, and I hope that you take the time and go through it, and good job.